So it's a great pleasure to be here. Thanks to the organizers for inviting me. And I'm happy to tell you about the first experimental results from our lab at Weizmann about long-lived quantum memories. I was going to do an introduction to motivate the use of bosonic qubits, etc. I think at this point, might be a waste of time. Instead, I'm going to do something more lighthearted and shamelessly promote Weizmann. And this is based on a couple of observations I've made during the past few days. First of all, at Weizmann, we have real coffee stirrers that are made with wood, and we keep pasta for food. Secondly, with all due respect to this very nice parrot, but I think that the mascot of Weizmann, which is a hoopoo, has a way more impressive crown. It's just an overall better bird, I think. And finally, I noticed some people like writing circuits from right to left. So at Weizmann, that's what we do, as we do with everything else. So please reach out if you're convinced. All right. And now back to business. I'm going to start by telling you a bit about the platform that we use for our memories and how we use it to make these supercharged cats. I'll talk a bit about something that came up a lot during this conference, which is error propagation between elements in your quantum circuits, and more specifically, propagation of errors from the ancilla transmon that you need to control your cavity to your memory mode. And finally, time permitting, I'm going to discuss the implications for quantum error correction. So we've seen quite a few of these cavities so far, and they've been around for more than a decade now, but they haven't really gotten better with time. And I can pinpoint 3 reasons that limit the performance of these cavities. One of them is that while they are superconducting, the surfaces are oxidized or full of contaminations, etc., and these cause microwave losses. Secondly, once you stick a chip inside, because you want to, in the end, control your quantum state of the cavity, you inevitably are going to introduce more losses by virtue of the Purcell effect, which just comes from the very coupling of the transmon mode to the cavity mode, but also just because of imperfections in your chip. And finally, the transmon is a noisy system. It's usually quite hot, and these fluctuations in the state of the transmon act as a measurement of the cavity state, and therefore these fluctuations will dephase your stored qubits. And all of these have kind of put a cap so far of a few milliseconds at most on coherence times of cavities. And we thought, why not try to surpass this limitation? Our inspiration came from wonderful work that was done in the community of particle accelerator physics, who've been making these superconducting cavities to accelerate particles for a very long time, and they've gotten really good at it. And more recently, the group in Fermilab showed that they were able to also make these cavities really good at low powers, which are not typically the case in accelerators. And they did that by, first of all, minimizing the surface to volume ratio. So if you have any contaminations on the surface, they will have less of an effect on your cavity mode. It also means that the mode volume is going to be bigger. Secondly, they use seamless design, something that the Yale group has also done. But in this case, they do it by electron beam welding. So you can imagine that this cavity is composed of 2 halves, and then you just weld the 2 halves together, which essentially eliminates the seam. And finally, they do quite sophisticated surface treatments. Most notably, they've shown that if you heat up this niobium under vacuum, the oxide is unstable and it will actually dissolve into the material. So you can get a much cleaner superconducting surface. And with all of these systems methods in place, they've shown a 2-second lifetime of a field inside such a 1 gigahertz cavity, which is really impressive. So it shows that we have a long way to go with our quantum our cavity qubits. By the way, feel free to interrupt me with any questions. I think I don't have that many slides. And Fermilab took that one step further together with the SQMS Center, and they decided that they want to build a quantum computer with this kind of cavities. For that purpose, they have built or they are going to build the world's largest dilution refrigerator called the Colossus. And then you can imagine that if you have several of these cavity modes and you use many, many Fock states in those cavities, you then have a high density of quantum information in, well, not a small system, but in a limited system. In our group, we're not going to make a quantum computer using these cavities. For one, our lab is 3 times smaller than this dilution refrigerator. But well, I do think that one can use these cavities to do better gates with higher fidelities. That's more of a long-term project. But in the very short term, you could use such a cavity in a hybrid setting as a quantum memory, right? You have transmons, which are very good at doing processing very fast. But then if you have idling qubits, and you're going to have a lot of these, you might want to store them in something that maintains the information for much longer. And I also hope that research on this kind of systems will trickle down and that people working on more scalable systems can learn some lessons from that. And finally, there's also the undesired side effect of really shifting the goalposts for people doing quantum error correction, which is it's going to be quite annoying. But we've talked about soft break even and hard break even. And I would suggest that there's the really hard break even, which means your quantum error correction gets you beyond the best coherence time of your class, right? Because of course, the better your qubit is, the harder it becomes to quantum error correct. A not so small detail with these cavities is that in the end, you've got to push a transmon chip inside it, and clearly, this is going to have a detrimental effect on the quality of your cavity if you're not very, very careful. And this is something that we in our group have thought a long time about. And the first design choice that we made in our lab is a very simple one. We cut this elliptical cavity in two, and I'm going to tell you why this is so beneficial. The downside is that now we've reduced our surface to volume ratio, increased the surface to volume ratio, and the effect of contamination is now going to be twice as large compared to the Fermilab cavities. On the other hand, now we can couple to the strongest field in this cavity using only a very small intrusion of the transmon inside the cavity, typically a millimeter or less. So we really minimize the exposure of the cavity to the chip. And finally, this design also is ultra-high vacuum compatible. We even have a load lock for a transmon so that we can keep the cavity under vacuum at all times. But for the experiments that I'm going to show you today, everything is done without this ultra-high vacuum feature. On the right, you can see a rendering of this system. You have it stopped working. So in red, you have the cavity mode. You can see the transmon chip sticking inside. And just to have a rough idea of the size, the diameter of our cavity is about 6 centimeters. Let's see. Nope. Okay. So, well, we made the cavity, and first we wanted to check the property of this cavity without inserting the transmon. And as a control, we started with very simple surface treatment. We've tried different kinds of etching, electropolishing, buffered chemical polishing, etc., but they gave similar results. And we were able to get, on the first try, basically, a classical lifetime of 110 milliseconds. So that's where we can get even with very minimal surface treatment. And one important lesson we can learn from that is something about the material that we use. Why niobium? Even if we assume that all of the losses in this cavity come from some resistance, some residual resistance of the niobium, we can bounce this characteristic to about 70 nanoohms. And in a very nice work by Rob's group at Yale, they've shown that aluminum has a residual surface resistance of 500 nanoohms. So it seems that niobium just has significantly lower resistance, which is one of the reasons that we can reach these high quality factors. Unfortunately, it's not going to stay that way. We've noticed that there is a degradation. And so most of the work that I'm going to show you, well, actually all of the results are going to be with this 30 millisecond curve. And we've done some work to understand what's going on and what causes this degradation. So one lesson we've learned is that it's not gradual. So it's not about some slow aging or oxidation of the cavity. And actually, we have some preliminary evidence, it's not really confirmed yet, that what causes degradation is mechanical stress. So once we attach the chip holder, even without a chip, to the cavity, just by screwing a bit too tightly, we think we might have introduced some micro cracks, which go away with etching. So you see, at this kind of timescales, you have to be very careful with details that you wouldn't have thought about otherwise. So we think that this shows that we can, we have ways to go still without even changing the system too dramatically. Yes.
So quick question. So does that mean this is stable? Like it just degrades to 30 milliseconds?
It doesn't change anymore unless you etch it, in which case it goes back to the original. But it also stays stable at this high lifetime. These were a few cool downs, and with decent exposure to air, if you don't attach the chip to it, which was quite a surprise for us. But this is still a bit under investigation, and we hope to confirm this soon. Yes.
Thanks. So from recent results on transmon, people have seen that, for example, using tantalum, the kind of oxide is cleaner than niobium, and then that led to a huge increase in P1s. Would you think that this will also apply for our 3D cavities, using like a block of tantalum to make a cavity? Do you think it could be even better?
Yeah, that's a good idea. One of the reasons we chose niobium is also that its oxide is maybe not a good oxide, but it's easy to remove, as opposed to the tantalum oxide, which is more stable, as is the aluminum oxide. So it was a conscious choice, but it's definitely a very interesting thing to try. And I do not know the residual surface resistance of tantalum, so that's another reason why this would be interesting.
Thank you.
Next thing is to put the chip inside with the transmon qubit, and that was actually the trickiest part. The first reason that it's tricky is because, as I said before, your transmon has to be really, really cold if you want to have a good coherence of your cavity mode. And that's because if it's not, it's going to effectively measure the state of your cavity. We were able to cool down our cavity to 0.1%, which then means that the transmon is going to get excited once every 100 milliseconds. The second thing that we had to do is to choose a very small coupling between the cavity and our transmon. And we've seen this in a few earlier talks, for example, by Philippe and from Yvonne's group. So going to this small dispersive interaction between the cavity and the transmon means that you're going to have less of a per cell loss. So if you think that part of the photon in the cavity lives inside the transmon, well, the smaller this interaction is, the less of it is going to live in the transmon, basically. And so the per cell limit in our case is about 278 milliseconds. Yes.
Question on one of your earlier comments, you say that you'd rather have the chip protruding less in a region where there is an intense E field, rather than protruding more in a region where there is less E field.
Mm-hmm.
Like, doesn't that balance each other? Like, is it true?
Yeah. In the end, you do want to have on the order of 10 kilohertz interactions in order to do good gates.
There's the participation of the chip in the purple electric matter. Like, does it make a difference? That is, I mean, but the actual volume is small, but in a region of intense issue.
Yeah, we can talk about this offline, but I think this is optimal. So this gives you a maximum coupling while there's minimal exposure to the sapphire. So we can talk about that a bit later. Right. The obvious downside of having a low coupling is that now it seems as though your gates are going to be really bad. And that is partially true. So the gates are going to be slower, but they don't scale with time. So in a few works, including my own in the past, we've shown that you can apply gates that are much, much faster than the time scale set by the dispersed interaction. And so we are able to encode a single photon qubit inside our cavity within only a microsecond. And that's 5 orders of magnitude smaller than the lifetime of the cavity. But of course, the limitation is going to be the coherence time of your transmon while applying this operation. All right, so here are the results of this single qubit encoding inside the quantum memory. So we put the qubit inside, wait, and then recover it and see how much coherence we have left. The lifetime of our qubits is about 25.6 milliseconds, and the coherence time turned out to be 34 milliseconds. This is not a hero device. We've tried with many different chips and a few cavities, different etching procedures. So this is a robust result. We can learn a few lessons from these numbers. One of them is that the coherence time is limited by loss. So 2T1 is about 50 milliseconds. But that's not so much smaller than the dephasing time, which is 100 milliseconds. And that definitely is going to just increase with time. As we improve our T1s, I think that photon loss and dephasing are going to be, competitive with each other. And in the later part of my talk, I'll mention how we should deal with it, in my opinion. We can also learn a bit more about features that are otherwise very hard to detect with these cavities. One thing we've heard a few times during this conference is that intrinsic dephasing of the cavity is very low. And we can confirm that. So we can infer from this data that the intrinsic dephasing is about 500 milliseconds. Intrinsic dephasing means dephasing that is not caused by transmon excitations. Yes. We encode a superposition of 0 and 1 photons and then decode it using this sideband drive. But the second thing that we've seen is that our cavity mode is also very cold. We haven't been able to measure the temperature, but we are able to put a bound on it of at least 5 seconds. So 5 seconds is the minimum time between photon excitations inside the cavity mode. So it really does seem like photon loss, single photon loss and dephasing are by far the predominant errors. What can we do with such a cavity? One of the interesting features is that, as we've seen many times, there is going to be a trade-off when you do bosonic quantum error correction. On one hand, you want as many photons as possible to get a code with good properties, good distance in some sense. On the other hand, the more photons you put in, the larger the probability is going to be that you're going to lose a single photon within your gate operation. And this kind of low loss cavity can really push you towards more higher photon occupations in the cavity. And so what we did is to encode, just as a proof of principle, a very large cat state inside our cavity. My students insist calling it chunk state. And what we're able to achieve is a cat state with the size of 1,000 photons. This is not the average photon number, it's the distance in photons between the two coherent blobs. And we could take this up to 2,000, at which point the dispersive approximation would break down essentially. The next thing we wanted to see is just to understand if the decoherence of these cat state scales as expected. And we expect that the more photons there are, well, the faster the decoherence is going to be. And we, in fact, expect a linear dependence between the photon number and the decoherence rate. For anyone who's hoping that with a 1,000 photon cat state, we would test or break down the standard model in quantum physics, and I have to disappoint you. Everything turns out well, even at 1,000 photons, and we have an exact or pretty exact linear decoherence rate. And what's interesting to see is that even with a cat state of 1,000 photons, the time of a single photon loss is about 54 microseconds, which is on par with the coherence time of an OK transmon. And in particular, it's still much, much longer than the time it would take to make a single gate operation. Where do we want to take this project from here? We think there's more improvements to be made. One of them is getting this mechanical damage out of the way. But of course, as I said in the beginning, we can do this vacuum heat treatment to further improve the quality factor of our cavities. We've tested this idea by Fermilab, and we've shown that we can actually remove the oxides from the niobium surface. We'll have to mitigate the Purcell loss. And finally, there's really no excuse at this point not to use echoed conditional displacement instead of dispersive interaction-based parity measurements. So this is something we're working on right now. Finally, as I said before, one important thing is going to be to get rid of this dephasing induced by transmon excitations. Because while we can increase the lifetimes of our cavities further and further, it's going to be really hard to cool down the transmon below 0.1%. So we have to take care of that. So as I said, we have about 100 milliseconds dephasing time in this half elliptical cavity. And at this point, we need to take care of both loss and dephasing. So we've done a few experiments with regular post cavities. What I'm going to show you is not done with the high coherence cavity, but the lessons that we learned can be used for that too. Oh yeah, nice animation. One way to get rid of the dephasing is based on work done at Yale during my postdoc, where we show that we can tune the dispersive interaction between the cavity and the transmon. And the way that we do that is by inducing with a microwave drive a dispersive interaction which has a negative sign to the negative sign and the same amplitudes or the same strength as the native dispersive interaction. And so effectively this cancels the interaction. So if you look at the T2 of the cavity without driving, which is much smaller than 2T1, once we are at this chi matching point, we recover almost all of the coherence of the cavity, as Rob showed in the slides yesterday. However, it's not entirely successful. There is still going to be a 14 milliseconds dephasing time in the system, and that's because when you jump to E, the interaction is canceled. But then when you jump from E to F, that's not the case anymore. You're going to still dephase. So we have to take care of that too. And so we're looking now at a complementary approach, which is quite intuitive, and that is to monitor the transmon very frequently and ask it all the time, are you in the ground state, are you in the ground state? And if not, apply pi pulse and reset it. So this is something that's been done in many experiments to reset the qubit, but we're going to show that it actually helps in increasing the coherence times of your cavities. So this is what the data looks like. In order for me to show that it works, I need to increase the thermal occupation of the transmon. So you see that if you don't do anything, your transmon is about 10% of the time in the excited state. However, when we turn on this active feedback, we're able to reduce this by more than an order of magnitude. And we expect that because the time spent in the excited state is so low, effectively the transmon cannot measure the state of the cavity, thereby improving the coherence time. And this works. So this is a T2 of the cavity without this active feedback on the transmon. And this is what it looks like when we measure quite frequently, once every 2 microseconds. We've also tested that this works for many different excitation probabilities or thermal occupation probabilities of the transmon. So this is a pretty robust method. It behaves quite well if you compare it to theory as well. But you'll notice that the recovery of coherence is not perfect. We only solve part of the phasing problem. And that's because the readout has a finite duration. And during that time, the cavity decays a little bit. So what you really want to do is measure faster and faster and faster. And you indeed see that you increase the coherence time as you increase the repetition rate of your measurements. Unfortunately, there's only you can only go so fast. And one thing that we're trying right now is to combine the two methods. So reduce chi and do some active feedback at the same time. And doing some simulations, you can see that it should be very, very possible to improve the dephasing time to a second. And we think that this will not pose a problem. And using these methods, we can actually show coherence times of cavities beyond a few hundred milliseconds, we hope. There is a caveat that I haven't mentioned, but I probably should, is that when you measure the transmon, you effectively increase its decay rate artificially. And one way to think about this is that you are also going to increase the Purcell loss of your cavity. And so this second method that I showed is a way to improve the dephasing time at the cost of reduced loss of your cavity. Before I get heckled by the theorists, I'm going to switch gears and talk a little bit about some theoretical insights, what we can learn from these things when it comes to quantum error correction. We've seen the slide before, I think in the first talk by Liang. This is work from this group with Victor and Kyungju. And they've shown that GKP outperforms all other codes when it comes to correcting photon loss. The question I would like to ask is this still true if you look at loss and dephasing, which we have to admit is a more realistic error model for cavities. Now you can talk about the loss dephasing channel without discussing the number of phase codes, which are a very elegant quantum error correction scheme from Arne, Josh, and Ben, which you can think of as the polar equivalent of GKP. So whereas GKP naturally protects you against displacements in the X and P quadratures, if you do a polar transformation, now you're going to correct against loss or excitation and dephasing errors. So this might be a more natural choice if you're dealing with both these errors. The way you do that is by encoding basically a generalization of the CAT code. So you have these multiple lobes in phase place, and you can think about the plus and minus states as being in between each other. So if you have a small dephasing error, you'll still be able to error correct against the dephasing. If you look at the complementary observable, its photon number, there's also going to be a separation. And so the code also naturally protects you against photon loss. A very elegant scheme to quantum error correct using this kind of encoding is with this trickle-down teleportation, which is something I learned from Vlad. So you can see here, if you take 3 cavities, you don't need to have 3, but simply to explain. And you do this kind of 2-qubit gate between 2 cavities, and then measure the state of the first cavity. You're going to teleport your number phase code or your logical qubit to the next cavity. However, controlled rotation, which is a kind of a CZ gate, commutes with dephasing. And so the dephasing errors is not going to be transmitted to your second cavity. On the other hand, if you have photon loss, that is going to be transferred to your second cavity, but in the form of a dephasing error. So if you repeat this once more, you also correct for dephasing. The downsides of this code compared to GKP is that you're going to need quartic interactions instead of linear interactions, gates, sorry. So GKP, the natural kind of operation are displacements, which are very easy and fast to implement. Here, the natural operations are rotations, which are more tricky. In order to understand which codes we really want to pick when it comes to correcting the loss dephasing channel, we need to understand the properties first. And so together with Chen Zhu and Liang, we set out to investigate the theory of this channel. And one thing that helped us a lot was to realize that the loss dephasing channel can be separated into first loss and then dephasing. And that's because these channels commute with each other. And this dramatically simplifies the picture. And using that, we can place bounds, lower and upper bounds on the quantum capacity. The quantum capacity is a figure of merit that tells you how much information you can transmit through a channel, through many uses of a channel. And this kind of puts a bound on how good your error correction can be. You could ask yourself, why don't we calculate the capacity? Why do we put bounds? Why don't we just calculate the capacity? Well, it turns out that whereas it's quite easy to calculate the capacity of photon loss, and recently also of dephasing, that's not the case for the loss dephasing channel. And that's because there is a very favorable property of the constituent channels that is not true for the combined channel, and that is the degradability. Degradability is a property that tells you that if you get some state from Alice, can you apply some operation to your state and get the state of the environment? If you can do that, the channel is degradable. And this helps a lot with the analysis of your channel. We were able to choose that this is not the case, and we were limited, therefore, to only discuss lower and upper bounds. Okay, so now we have a benchmark. We know what to aim for. Let's now look at the codes, the error correction codes, against varying loss and dephasing. This is a nice kind of phase-based picture we've made of the optimal codes for varying loss rates and varying dephasing rates. And it turns out that there's kind of the stepwise behavior. As you move across this picture, you jump from one kind of code to another in a pretty discrete way. When you look at the edges, there's no surprises. We already knew that if you have dephasing and no photon loss, you're going to want to use the two-legged cat codes. Right? As has been done by Nick and other people at Yale and France. They've all used this two-legged cat code to correct against dephasing. If you look at the other extreme, where you have only photon loss and no dephasing, that was also known that GKP performs better than other codes, even though a bit counterintuitive because GKP protects against displacements more naturally, but it turns out to be really good against photon loss. What's more interesting is that in between these two extremes, you get a whole different kind of codes. The first thing you should know about these is that unlike the cat code and GKP, you don't want to have as many photons as you can. So no matter how many photons we allow this code to take, it'll pick some fixed average photon number occupation for its code. And you'll know that some of these codes are very similar to a code that has been shown before by the group of Liang, which are numerical codes that have been obtained in a very different way. You also might know that some of these codes have rotation symmetry. So this suggests that these codes are similar to the number phase codes I discussed earlier. But it turns out it's not exactly the case, because while there is rotation symmetry to these codes, the Z operator, the logical Z, is not the half a rotation, okay? So whereas, the logical 0 and logical 1 are separated by some angle, which is half of the symmetry angle, this is not the case for the codes here. So these are not exactly rotation. All right, now we can take those codes and compare them to the quantum capacity bounds I've shown before. So in gray, you have the upper and lower bounds of the quantum capacity. And we've taken the families of codes that we've talked about so far and put them against each other, see who performs best. My aim was kind of to show that GKP is really bad at correcting dephasing errors, and I ended up proving the opposite. It turns out that although if you look at the entanglement fidelity, how well GKP performs if you send in a state through the channel, that does not mean that its capacity to store information is less good. In fact, it is very close to our optimized states, the numerically optimized states for all parameter regimes. And it sometimes even exceeds the numerically optimized codes. That again shows you that the capacity to store information or transmit information is different to maintaining a high fidelity. And we know that's true. Think about biased error correction. Right? Sometimes it's worthwhile to add a bit more noise, but as long as that noise has structure, you can then add an upper code, an outer code, which will use that structure to get better information storage. So that's one lesson we learned. And you also see that the CAD codes, which represent the class of rotation codes, is much lower in its capacity to transmit information. And that's mostly a consequence of the fact that these states are less packed. And so it's less compact encoding, which means it'll be less good in transmitting information. So bottom line, don't discard the GKP yet. With this, I'd like to thank the many students who participated in this work, specifically Ophir and Bakai and Nitzan, who worked on the cavity qubits, Uri, who did the active feedback protocol, and Peter, who did the theory work. With this, I thank you for listening, and I'll be happy to take any questions. For questions?
How'd you calculate the capacities? Because we did them from the fidelities. What did you do?
How did we calculate this figure?
Yeah.
Yeah, I forgot to mention. What we calculate is actually a lower bound on the capacity using the hashing bound, which is very similar to what you used in your paper.
Okay.
So these are hashing bounds on the different codes.
You see more drastic differences than we did with this GKP outperforming. We tended to see similar. If the fidelity was lower, then the capacity would also be lower, but somehow.
Yeah, so we see that this is not the case.
Yeah.
And this remains true even if you go to high dephasing, which is quite surprising.
Right.
Yeah, thank you for the talk. Can you go just like one slide? Yeah. So regarding like the fact that these codes are numerically optimized, and in particular with regard to what you said after that GKP could not perform so bad compared to what we could see. A natural question is that since this is numerical optimization, how much could be explained by the fact that you are just exploring like different local minima?
The problem of optimizing these codes is not a convex problem. This is also a result of what I said before, that it's not a degradable channel. That doesn't help. However, we've seen that for these parameter regimes, for different initial choices of initial codes, you converge to the same type of code. And this happens consistently every single time. When it doesn't happen, we put this gray box here. So here the landscape is so shallow and the fidelity is so close to 1 that you convert to different codes for different initial points.
For instance, if I just add one thing. For let's say if you started on the upmost left thing where you see the cat. Oh no, let's not say for the cat, but at the rightmost top thing. Let's say if you initialize voluntarily in a GKP code, do you see the convergence?
I don't think we've tried that. I think we start with random codes. It's maybe worth a try.
Hi, question about the active reset scheme for maintaining the transmon in its ground state. I thought maybe a concern about that would be if your readout has some errors, then you're like repeatedly checking it's in G, but maybe you accidentally see it's in E and then you invert it. So what would that not be like a limit that might be similar in scale to what thermal population you could otherwise achieve?
Yeah, that's a very good point. When you have some readout error, you can think about having these two Gaussians. What you really want to do here is to choose the thresholds in such a way that when you're in the ground state, you for sure get G. So we give up a little bit on the fidelity of detecting an excitation that we gain in not introducing intentional errors.
Okay, makes sense. Yeah.
I just had a quick question about the numerical rotational codes. You said they don't have like Z as a logical operator. Do they have any like logical operators like in terms of these simple operations?
Oh, that's a good question. I think not, but I would have to think about that a bit further.
Thanks.
Yeah, in all of these optimizations, we ignore the ease of initializing and decoding and error correcting. So this is just about the very, the ability to transmit information through a channel. And we haven't looked closely at the schemes for each one of these encodings.
You say that when you measure your transmon, you get essentially T1 versus N bar, and that this will induce more per cell losses, even if your transmon is in G. Let's say we make a thought experiment where I crank up the readout power to the point that my transmon lifetime degrades, and I measure it continuously, and it's always in G. Does the T1 of the cavity degrades too?
Okay, what I meant, and we haven't observed this experimentally, is that it's not about T1 versus N bar. I hope everyone is fine and healthy. What I meant to say is that because of the hybridization between the cavity and the transmon, sometimes you're going to measure E, not because of thermal excitation, but because you kind of collapse the single photon in the cavity to the transmon, right?
But why is this assisted by your measurement? If your measurement is coupling is dispersive?
Because the measurement dephases, right? And this is something I probably didn't say. When you think about per cell loss, you don't have to think about decay of the transmon causing decay of the cavity. In fact, even just dephasing of the transmon induces per cell loss. This is called just dephasing. So I've had a few discussions with a few people about this. So the very measurement of the transmon collapses the excitation, thereby removing it from the cavity and inserting it into your transmon. And then it basically gets reset. We can take this offline, and it's a tricky point.
Yeah, hi again. You said on the something like the saturation of the photon number that for the pure loss or pure dephasing errors, you are like the optimal code saturates the maximum photon number. And for the pure loss, like intuitively, I would think that since the photon loss like amplitude gets higher and higher, the further you go in space, you would have an optimal value of the size of the code. Do you have any way to understand why this intuition doesn't work?
Yeah, that's a good question. Not sure I have an answer. Maybe one of the GKP folks want to say why that happens. Basically, when you add more and more photons, you narrow the peaks, essentially.
That known, or you? So the backstory of this question is that, for instance, for our dissipative stabilization scheme, we can show that there is an optimal photon number. So my question is also like, is this increasing to GKP or a failure of our scheme?
So this is what we see in our simulations, and I think this maybe Liang, you want to say something.
So what we find for the GKP optimization, if it's loss only, the performance increase monotonically as you increase photon number, and basically infinite GKP is good.
But why? Yeah, the question is why is that the case? Since if you increase more and more, add more and more photons, you basically increase photon loss.
So one explanation is probably not for optimal recovery. It's just that you can do amplification and recovery, right? And that's the noise that if you get infinite GKP, you get extremely sharp like this, like those spots, and you can correct more errors by having larger GKP. Yeah. But of course, that's not optimum recovery procedure, but at least to show that the larger the code, and at least for that particular recovery, you get a better performance. Yeah. And also,
and this is optimized for any recovery.
That's right. Yeah, but this is optimized for any recovery, and also for our transpose recovery, we actually proved that's actually monotonically increased. At least numerically, it shows monotonic increase. And asymptotically, we take the limits. If that limit taking order properly, you can show it approach that performance.
But I assume there's diminished returns as you increase the photon number more and more.
Yeah, it was a surprise actually when Andrew found this about 5 or 6 years ago. We were kind of surprised. Oh, well, surprising. You have more photons that helps. The difference is it's different from CAD code because CAD code only uses one-dimensional space, kind of quasi one-dimensional on the ring, while GKP uses 2D, which is effectively some thermal encoding. It turns out that actually helps a lot.
Thanks, Larry.
Yeah.
You should change the way you decode, and you should also change the way you error correct.
Yeah, well, I think you need to choose the right way to do the decoding, so that as the code goes larger, you probably need to make sure that takes in that.
But again, this is an intrinsic property of GKP. It has nothing to do with the type of encoding.
So can you extend this result to error correction, to also modify the way you do error correction?
But here, first we already fixed the encoding, fixed the error channel. The only thing is about decoding, which I guess that's what you mean by error correction, right? And this one, yes, you can optimize it when you have a larger logic.
So this one is it's what's called a biconvex optimization. So we optimize for the decoding and then for the encoding, and then we get for the decoding, inspired by Kyungju's earlier work.
All right, we are out of time. Let's thank Serge again for the